So when people start talking about omega-9s and omega-7s and omega-11s, don't listen. It is, the research on omega is on a set of very specific fatty acids. First of all, a little primer on fatty acids. These are the four main classes of fatty acids that you will come across. It's the saturated fatty acids that have no double bonds. It's the monounsaturated fatty acids like oleic acid. It is the polyunsaturated, and then we have the long-chain polyunsaturated fatty acids. The first two of those are basically food. The last ones, the ones with structure, are structural elements in our bodies, and they occupy our membranes. And then here comes what most of you call the omegas, but it isn't any omega. It isn't alpha-linolenic acid. It is the short-chain varieties. It's specifically these three fatty acids: EPA, DHA, and DPA and DHA. And they have systematic Greek names, and they're just named according to their structure. But all the research done on the health and biological effects of omegas is connected with these three substances. Nothing less, nothing more. So, why are they so important? Well, we really can't make much of it in our bodies. So they are conditionally essential. We can transform a little bit of alpha-linolenic acid into EPA and DHA, but as you can see on the left-hand side here, it is very little that ends up, for example, as DHA. So that's why we need to eat it. We need to get it from seafood. And isn't it beautiful, really, that what is made mainly by microalgae in the oceans are absolutely necessary for humans. So we are really directly connected with the most primitive form of life on the planet. So how do all the omega-3 fatty acids do their complex biological effects? How can such a small collection of molecules have so many different biological actions? Well, first of all, they reside in the membranes, don't forget. So, the first effect they have is directly on the membrane. The membrane needs fluidity, the membrane needs to accommodate rafting, the membrane needs to anchor everything that is inside the cell that needs to be anchored to the membrane. And the amount of omega-3 fatty acids, because they're bulky, actually direct the fluidity of the membrane. Then they also actually directly interact with our genetic mechanisms. So they will influence transcription factors both directly and also the prevalence of transcription factors. And now, most importantly, our cells needs to talk with itself. It needs to talk with its nearest neighbor. And how does it do that? Well, it partly does that through what we call lipid-derived signaling. And you've all heard about prostaglandins and leukotrienes and the similar eicosanoids. But there is a large class of these molecules, and they are all extracted from the lipids that sit in the membrane. They're made there when necessary. They're part of the inflammatory response. Now, when you put on an inflammatory response, then there is a time-fused situation where it also needs to be shut off. And it's the same molecules that float downstream that do both the on and the off. So we have the classic eicosanoids, and then we also have what is called slow-resolving mediators. They actually switch off the signal. And then also, let's not forget, we have new classes of what we call not classical eicosanoids. The endocannabinoids are probably the most prevalent signaling system in our bodies. And then there are a number of other novel substances that have the same. So let's have a look at what a phospholipid membrane looks like. So here's a cell, And then, of course, we have the phospholipid membrane. It's a bilayer, and it's a fatty layer in between two water-liking layers. And as you can see, in the membrane, we have omega-6 fatty acids, and we have omega-3 fatty acids. The top omega-6 is dominated by arachidonic acid, and omega-3s are dominated by EPA and DHA. Now, there is, the importance here is that while the omega-6s and the omega-3s are being processed by the same enzyme to make those signaling molecules, COX or LOX, and a few others, then the omega-6s give the classical class of prostanoids. Now, the omega-3s will give the sister class, and they're actually distinct different molecules, and typically the omega-6 class have high inflammatory activity, and the omega-3s have lower inflammatory activity. So, the long-chain omega-3s are not anti-inflammatory, they are modulators of inflammation, and it's meant to be like that in a healthy cell. So what makes krill oil different? Well, krill oil consists of omega-3 fatty acids bound to two different types of molecules, triglycerides that you know from regular oils, and phospholipids that I recently talked about. The phospholipids are what makes us. It's actually, it's hard to overstate how important the phospholipids are because we're all made of it. Every single cell is wrapped in phospholipids. We tend to think of ourselves as protein, but we're actually more phospholipid membranes. So, and that's what sets krill oil apart, because it contains not just the triglycerides, which is the regular one, for example, in fish oil, but it contains both, and in a pretty much 50-50 ratio. So, and then of course, since it comes as a phospholipid, it also carries with it what is called the head group on the phospholipids. In krill oil, it's the choline. So you actually, by taking krill oil, you're getting the omegas, but you're also getting phosphatidylcholine. And remember, that's different from eating the choline salt. The choline salt is good food for bacteria in your stomach, and it will be broken down in your stomach and taken up as TMA and then excreted as trimethylamine oxide. That doesn't happen with phosphatidylcholine. There is a specific uptake mechanism for it, together with the omegas, by the way. So, what's the difference then? Triglycerides, it is mainly storage of energy. That's the general use of triglycerides in nature. And it's exactly like that with us. That's why we get fat. While the phospholipids is all about structure. And having the right fatty acid in that structure is absolutely necessary for a well-functioning cell. So, I don't know how much you know about the physiology of the uptake of lipids. I actually lectured this for 15 years, and I never told my students anything like this, because it's actually quite new knowledge. But the regular way of uptake of fats is that it is being digested in the stomach, it is then taken up in the stomach and in the gut, it is emulsified, it is broken down into free fatty acids, it's then made into chylomicrons, it's taken up in lymph, and then it is dropped from lymph into the general circulation in vena cava. Now, so it hits all of the body before it hits the liver. And for many years, this was the eternal truth. Now, with the phospholipids, we realized that you can take off one fatty acid, you get a lysophosphatide, it is water-soluble enough to be transported directly through the liver through the hepatic circulation. So, when you take an omega-3 that sits on a phospholipid, it is actually taken up differentially from the triglycerides. It hits the liver first, and it is processed in the liver for delivery to the tissues, differently than from the other forms. Now, this curve is from a human, where it was given a large dose of krill oil, actually, and this is what it looks like when you look for EPA in plasma over the first 3 days. So here we have a food. Let's say you have a meal of salmon or sardines. And you eat it, and you reach the maximum concentration of plasma in about 7 to 12 hours. And it washes around in your blood and plasma for 3 days. That is not the distribution of food. These molecules are heavily redistributed and utilized by your body. So this is not, if you had put in here regular fats, like palmitic acid or the similar, you would see that they're taken up in about 2 hours and they're excreted, they're utilized in less than 10 hours. That's not the case with those precious fatty acids. So, one thing, how is this transport going on? Well, we didn't know until the summer of 2014 when this paper came around. And this paper told the following story. It's through what is called knockout mice. They found that a specific transporter called MFSD2A, part of a superfamily of transporters, was absolutely necessary to transport any fat, including DHA, into the brain. So until then, we believed that it was some sort of magically flowing into the brain over the blood-brain barrier, although it's not water-soluble. But now we know that the transport into the brain is through this transporter. Now, this transporter sits somewhere else too. It sits in the gut. So that's why we know now that it is taken, that certain molecules are taken up directly there. It sits in the liver. It sits in the placenta. So this is also the transporter responsible for taking DHA over into the child of the childbearing, from the childbearing mother. Now, this piece of research also showed something scary. When you knock out this transporter, then you see the wild-type mice with big brains, and you see the smaller brains of the knockout mice. And I'll leave it with there. It is absolutely essential for life. If you knock out this one, you will die. So, I've already mentioned this. So, how do we measure the omega-3 level in our bodies? Now, I showed you the plasma concentration curve. If you're going to measure the amount of omega-3s, then you would have to fast for 3 days. Not a good option. And it really is very messy to measure plasma concentrations of, so you need to measure some sort of tissue concentration. That's not easy. Fortunately, it turns out that you could do it by measuring the relative amount in erythrocytes. The only fat that sits in an erythrocyte sits in its membrane. And the omega-3 index is simply the relative amount of EPA and DHA and EPA in your erythrocyte membrane. And a lot of research has been done over the last 20 years that shows that you should be in the neighborhood of above 8%, at least somewhere between 6 and up. And for different conditions, different amounts are necessary. And just to prove my point, if you measure the amount in the erythrocyte and compare it biopsies from myocard, you get a clear linear correlation. And this is, I could have shown you in animals, there are many, many other tissues that are exactly the same. So measuring the amount in the erythrocyte is a valid measure of your steady state total body concentration of EPA and DHA. And it's a good measure. So, knowing that, what does it look like throughout the world? This came out about 2 years ago. And it shows the red part here is where the level is down at less than 4%. The green is where it's about 8 on average, and then there is everything in between. I'm glad to see that my home country, Norway, is on the 8% range. You shouldn't be too glad to see that Brazil is in red region here. Anyway, also recognize Mongolia, the blue one, which is actually doing quite well. And they eat no seafood at all. But they also only eat grass-fed meat. And their genetics are obviously different. So they're able to make some DHA. So, with the omega-3s in general, then you have a number of health conditions that are being influenced. The most well-known is on the heart health. Increasingly, we are looking at brain. Don't forget your eyes. Every time you open your eye, you lose about 2,000 DHA molecules. And it doesn't help to keep your eyes closed either. And then, of course, in the immunological systems, as I've told you, one of the primary mechanisms of regulating the inflammatory response, which of course is part of the immunological responses too, is through changing the fatty acid or the fat content in your membranes. This is just a diagram of the research that my organization, Aker BioMarine, has been doing through the years on the different health fields, as well as on the more fundamental biochemistry. And as you can see, we have a number of large projects going on, and they're all, what links them all together is actually inflammation. So let's have a look at omega-3 fatty acids and physical activity. I don't know how much you know about diseases among people who have heavy exercise, or like real sports people. You may know that football players, as well as swimmers, have a higher incidence of certain cardiac death than the regular population. And they usually get this very early in life, like in the 20s and 30s. Now, there is a curious link to the omega-3s. Well, first of all, we did a study where we looked at performance. And we basically looked at what happens in a very heavy exercise with regards to inflammation. And we did find that there was a change in the expression of interleukin-2 and also in the recruitment of NK cells. Both are important mediators of repairing the tissue after you have heavy exercise. So we teamed up with something called the Norseman, which is a triathlon taking place in Norway. You swim through the fjord, you bike through the hillsides, and then you climb a mountain in the end. And it's a dreadful experience, I guess, for those who do it. So this is what's going on. They jump out in the middle of the fjord. It's cold, and it's quite demanding. So when we looked at the omega-3 index on those who did Norseman, we found, as expected, that their omega-3s are low. We have found it consistently with all sports people. But we also found that those who had a higher level had the upper hand. They actually won the race. And we found that the omega-3 index was the one factor outside of exercise that predicted their performance. So also another thing we found was after this heavy exercise, the levels of DHA was reduced for several weeks after. So they really need to be replenished. And also, we found that if we supplemented them with krill, we could reverse this effect. Also, quite interestingly, those who had the higher levels already regained their strength faster than those without. So if you had a high level of omega-3 index, you were able to start training again several weeks ahead of those who had low levels. But clearly, it is an important factor in your capabilities as a sportsman. So let's jump over to women's health. Now, the first thing here to mention here is that we found a very strange thing early on when we looked at the uptake of the omega-3s in its phospholipid form compared with in its triglyceride form. Women seem to take it up better than men. You see no such thing with fish oil, but with krill oil, clearly women were utilizing it better than men. We really didn't understand why. I don't think we still understand it, but it's a clear observation, and others have made the same observation. So, an old study that came out many years ago, ahead of my company, showed that in premenstrual syndrome, krill oil seemed to be alleviating some of the symptoms and some of the pain. So both pain and depression, as well as the feel of pressure. And so we set up a study with placebo-controlled and in different doses. And actually, we reproduced the effects that were seen in the other study. The other study wasn't well controlled, and our study was. So, yes, it seems to be real. It seems to be an effect. It's an alleviating effect. It's not taking it completely away, but it makes it easier to live with it. So, then what about children, and what about pregnant women? So, well, we know that the omegas are really important in this part of life. Now, we also know that there is a link between premature birth and the high level of DHA, and it's actually quite significant. We also know that this is a study from Denmark that show that if you have a high level of DHA during the pregnancy, the risk of the child to suffer from wheezing and early asthma was down by almost 50%. It's also been shown that, and this actually is a study from Norway, my home country, that showed that the level of DHA prior to birth actually is correlated with the baby's ability during the first year to solve problems. So intelligence, really. And then let's not forget about the mother. The chances of postnatal depression is higher in women with low levels of DHA. Just very briefly at skin, let's jump this one. We have done a few studies on skin, where the one confirmed the other one and the placebo control. What we did was basically to compare the placebo and the krill group, and what we found was that hydration of the skin and dermal water loss is reduced in the group that took the phospholipid krill oil. And also in cognition, I'll leave this one, you all know that DHA is very prominent fat in your brain, both in the central parts as in the cortexes. We found early on that the uptake into brain of phospholipid-bound omegas were better than in animal express than the triglyceride form. Now, knowing what I told you with the MFS, the 2A, that shouldn't be surprising. So again, the first study that came on from the group that did the MFS, the 2A, was on animals. This is the human equivalent. And what they showed is that I found 4 mutations, and I found that if you have this mutation in your MFS, the 2A, you basically are born without a brain. The brain is completely devoid of fat, and it's of course completely dysfunctional. One child survived and confirmed the results from the rat or the mice experiments. So we'll leave that one. And then just to explain this thing about MFS, the 2A. Now, what's the clue here with krill oil? It is not the fatty acid itself that is absorbed, but it is the fatty acid that sits on the lysophosphatidyl-choline. So you need the fatty acid to be part of lysophosphatidyl-choline to be taken up into the brain and certain other deep tissues. This is just on cognition. Just 2 words on what I believe is going to be one of the large epidemics of the modern world, non-alcoholic fatty liver. You haven't heard about it because you can't really diagnose it easily because you need a biopsy of the liver. Now, methods are now coming, composite methods, that makes it possible to diagnose the condition without a biopsy, and it will explode. Maybe as much as 60% of Americans suffer from non-alcoholic fatty liver, and it is pre-disease. You can do something about it. So this is healthy liver to non-alcoholic fatty liver, then it progresses downstream to steatosis and metabolic syndrome. But by taking omega-3s and by taking phospholipid-bound omega-3s, that is phosphatidylcholine, you can actually reverse, hopefully, this before it progresses down into the disease. And then this is just a study we've done on cognition, where we have involved the American military to see if they are better suited to tackle their stress, and they take Krylov. The results will be out quite soon. And then another inflammatory disease, namely lupus, and we are now in a large clinical study program with the Lupus Organization in the US to see if we can alleviate some of the inflammatory related distress that these individuals experience. And then, obrigado.